So average precision is computed for just one query, but we generally experiment with many different queries, and this is to avoid the variance across queries. Depending on the queries you use, you might make different conclusions, right? So it's better to use more queries. If you use more queries, then you would also have to take the average of the average precision over all these queries. So how can we do that? Well, you can naturally think of just doing arithmetic mean, as we always tend to think in this way. So this would give us what's called a mean average precision, or MAP. In this case, we take arithmetic mean of all the average precisions over a set of queries or topics. But as I just mentioned in another lecture, is this good? Recall that we talked about the different ways of combining precision and recall, and we concluded that the arithmetic mean is not as good as the F measure. But here it's the same. We can also think about the alternative ways of aggregating the numbers. Don't just automatically assume that let's just take an arithmetic mean of the average precision over these queries. Let's think about what's the best way of aggregating them. If you think about different ways, naturally you would probably be able to think about another way, which is geometric mean. And we call this kind of average GMAP. Right? This is another way. So now, once you think about the two different ways of doing the same thing, the natural question to ask is, which one is better? So do you use MAP or GMAP? Again, that's an important question. Imagine you are again testing a new algorithm by comparing it with your old algorithm in the search engine. Now you tested on multiple topics. Now you've got the average precisions for all these topics. Now you are thinking of looking at the overall performance. You have to take average. But which strategy would you use? Now first, you should also think about the question, would it make a difference? Can you think of scenarios where using one of them would make a difference? That is, they would give different rankings of those methods. And that also means, depending on the way you average, or you take the average of these average positions, you will get different conclusions. This makes the question become even more important. Right? So which one would you use? Well, again, if you look at the difference between these different ways of aggregating the average precision, you will realize in arithmetic mean, the sum is dominated by large values. So what does a large value here mean? It means the query is relatively easy. You can have a high average precision. Whereas GMAP tends to be affected more by low values. And those are the queries that don't have good performance. The average precision is low. So if you think about improving the search engine for those difficult queries, then GMAP would be preferred, right? On the other hand, if you just want to have improvement over all the kinds of queries, or particular popular queries that might be easy, and you want to make it perfect, and maybe MAP would be then preferred. So again, the answer depends on your users' tasks, and their preferences. So the point here is to think about multiple ways to solve the same problem, and then compare them and think carefully about the differences and which one makes more sense. Often, one of them might make sense in one situation, and another might make more sense in a different situation. So it's important to figure out under what situations one is preferred. As a special case of the mean average precision, we can also think about the case where there is precisely one relevant document. And this happens often, for example, in what's called a known item search, where you know a target page. Let's say you want to find the Amazon homepage. You have one relevant document there, and you hope to find it. That's called a known item search. In that case, there's precisely one relevant document. Or in another application, like a question answering, maybe there's only one answer there. So if you rank the answers, then your goal is to rank that one particular answer on top, right? So in this case, you can easily verify the average precision will basically boil down to reciprocal rank. That is 1 over R, where R is the rank position of that single relevant document. So if that document is ranked on the very top, R is 1, and then it's 1 for reciprocal rank. If it's ranked at the second, then it's 1 over 2, etc. And then we can also take a average of all these average precision or reciprocal rank over a set of topics. And that would give us something called a mean reciprocal rank. It's a very popular measure for known item search or any ranking problem where you have just one relevant item. Now, again, here you can see this R actually is meaningful here. And this R is basically indicating how much effort a user would have to make in order to find that relevant document. If it's ranked on the top, there's no effort that you have to make, or little effort. But if it's ranked at 100, then you actually have to read presumably 100 documents in order to find it. So in this sense, R is also a meaningful measure. And the reciprocal rank will take the reciprocal of R instead of using R directly. So one natural question here is, why not simply using R? Now imagine if you are to design a measure to measure the performance of a ranking system when there is only one relevant item. You might have thought about using R directly as the measure. After all, that measures the user's effort, right? But think about if you take an average of this over a large number of topics. Again, it would make a difference, right? For one single topic, using R or using 1 over R wouldn't make any difference. It's the same. Larger R would correspond to a small 1 over R. Right? But the difference would only show up when you have many topics. So again, think about the average of mean reciprocal rank versus average of just R. What's the difference? Do you see any difference? And would this difference change the order of systems in our conclusion? And it turns out that there is actually a big difference. And if you think about it, if you want to think about it, and then yourself, then pause the video. Basically, the difference is if you take a sum of R directly, then again will be dominated by large values of R. So what are those values? Those are basically large values that indicate lowly ranked results. That means the relevant item is ranked very low down on the list. And the sum, that's also the average, will be then dominated by where those relevant documents are ranked in the lower portion of the ranked list. But from a user's perspective, we care more about the highly ranked documents. So by taking this transformation, by using reciprocal rank, here we emphasize more on the difference on the top. Think about the difference between 1 and 2. It will make a big difference in 1 over R. But think about 100 and 101, it won't make much difference if you use this. But if you use this, there will be a big difference in 100 and let's say 1000. Right? So this is not desirable. On the other hand, 1 and 2 won't make much difference. So this is yet another case where there may be multiple choices of doing the same thing, and then you need to figure out which one makes more sense. So to summarize, we showed that the precision recall curve can characterize the overall accuracy of a ranked list. And we emphasized that the actual utility of a ranked list depends on how many top ranked results a user would actually examine. Some users will examine more than others. And average precision is the standard measure for comparing two ranking methods. It combines precision and recall, and it's sensitive to the rank of every relevant document.